Okay, everybody, let's start again. Okay, what we've seen so far is an algorithm that helps us if we have this. What we've seen so far is an algorithm that helps us to determine the best value that one of the players can achieve according to this min-max algorithm by just maximizing the value that it can achieve by every move by knowing what the minimum value is of your opponent. So the worst case scenario you take into account and then you maximize over the worst case scenario. But that is on the basis that we know that at the end of the tree, we come to the solution of the game. And of course, in many of the games, this is impossible. So in chess, a game can be, hundreds of moves. It can in principle, continue infinitely. Or no, I don't think it can be really, really long. So it's impossible to go all the depth to the point where you know the value of each of the whether you win or you lose. So we need to do something about it. And what we have done so far, as I said, is really supposing that we know at the end of the path what the outcome of the game is. But in real games, this is impossible. So now we have to replace the decision on whether a node, when you win or you lose, from the real end of the game to an earlier stage. Because otherwise, we will never be able to apply the strategy for real games. So basically what we have to do is we introduce a fixed depth limit. And so that's common practice in these games implementations. So you basically have to say, I'm looking forward I'm looking ahead in my game for, let's say, 5 moves or 10 moves. This is not needed in Schnapsen because we only have these 5 moves at the end, and as I said, we only have few states in the second phase of the game. But for any other game like chess or the more complicated ones, we really need that. We will see later that the problem of the uncertainty is a different one. So for phase 1, this doesn't really apply. The depth of Schnapsen is only 20 if you take your opponents into account, or 10 own cards that you can play. So that is really very limited. But in the other games, we have to sort of do a cutoff. And then basically what we get is that at a certain cutoff, looking ahead, we have to apply some heuristics which tell us how good the state is we're getting in. So we have to make an estimation over, let's say, n steps that we look ahead. How good is the position that we get ourselves into? And that becomes now the algorithm of min-max, not with a utility state, where we know the result, but with a heuristic estimation value. For the rest, this is exactly the same. Yeah. So we apply now the value of at a certain point, how good is this state? And if we don't know whether this is a win state or a lose state, we just estimate what it is. So the utility value is the value based on the quality of the states. So you win with an inning of 3 wickets. Player X has 33 points, player I has 69 points. This would be the utility value of the game, on which you can determine whether the game is won or lost. The alternative now is to go for heuristics. And the heuristics tells us, for example, the classical chess heuristics that you learn as a starting chess player, that 2 pawns and a bishop is stronger than a castle. These kind of calculations, I think you give 3 points to a bishop and a pawn, and a pawn is 1 point, and a castle is 5. So I think this heuristics isn't really correct, but these kind of calculations that you make of how many figures on the chessboard have you lost and how many do you still have. Another one is in Schnapsen. that playing the trump ace is better than a random jack in the beginning. That would be a heuristics that we apply, and it probably, again, in Schnapsen, it's in phase 1 is not a good choice. If you are in phase 2, where the opponent has to follow your card, your color, then playing the trump ace is a very good heuristic. So you see that it depends very much on the situation. So finding the right heuristics is one of the big tricks of developing a good game algorithm. For the rest, the thing works precisely the same way. So we say there is a cutoff of level, in this case, what is it, 3 or so, and there is a huge tree underneath maybe. Maybe we could play a long game in this situation, but somehow we decide that on a certain level we stop with the search and we then apply the minimax algorithm again. And we apply it in exactly the same way. So if we have these two states, then and Max can choose on this level, then it would choose the 3, this one it would choose the 9. But now these values that we have, they are not the true predictions of it will win or it will not win, but they are predictions of how good will the state be after a certain level of search. In a way, this is moving from perfect information to imperfect information, because we say after some level we do as if we don't know how things go on. So basically we paid the price for being within a reasonable amount of time by working with approximate reasoning. So sacrifice perfect information for performance. That is a choice that has to be made, and that has to be made in many of the AI applications that you are going to build in your life. So now we have the heuristic evaluation function for a heuristic minimax algorithm. And as Frank showed you yesterday, building these heuristics is really one of the biggest tricks in building good AI systems. And basically what you try to do is to try and find an estimation for a game position that is as close to the real winning of this position. So give a position, how can we estimate whether it really is better than another position in terms of getting us to a goal state? And the performance of your game engine depends very, very strongly on the choice of this heuristic. So it shouldn't come as a surprise that for the practical assignment, for the bots that you're going to build in this course, finding good heuristics is a really interesting way of doing the research. So think of anything you know about the Schnapsen game, and that's why I really pushed you to practice the Schnapsen game, because in the short days of your playing, you will already have seen, hopefully, some of the strategies that work and some of them that don't work. So how can we now have a machine that uses those heuristics to play properly? And this only works if you have some kind of environment where you move in your states in some slow way, in a way where you transform without heavy swings. So Quotient, can't even pronounce this word, swings in the values of your evaluation function. So as I said, there are many strategies, and there are also many heuristics that you can have about certain states. So what experts in the field then have to do is to look at the different state positions and to decide for, what makes this a good position. And what you have in the beginning of chess, you should have a 50-50 chance, so you should really have a function that doesn't make a difference between these two positions. And at the end, when you have a winning position, it should be zero value, or it should be the maximum value that you can achieve, the winning. And then the question is, how can we find a function that defines values in between those starting value of uncertainty, full uncertainty, to the winning or not? And one of the common strategies in chess is just counting the number of figures that have been taken out of the game. So here we have 2 pawns and a castle and 2 more, so they have exactly the same number of figures that are out of the field. But then I think it says white is about to lose, and I'm not seeing exactly why this is the case.
Why does black lose the queen? Horse, black horse.
Yeah, so probably you can get yourself with the queen in a very good position. So probably you could count the number of blank fields around your king. So testing the defense of your king. So here the king is in a very good defense, but still the other figures are not that developed that far. So here the valuable figures are further out of your own position from the white ones. So each of those positions have a different strategic evaluation. And what you do in order to calculate one value that makes in the end the decision for which move to make is to combine all those different evaluations that you can attach into one heuristic function. And then you give it some weighting. So you think, okay, if you have more of the figures, then this is more important rather than the development of the main figures of the game. Yeah. And of course, building this evaluation function that estimates the quality of the moves is a really complicated thing, and it takes a lot of time. It takes a lot of fine-tuning and so forth. And there are many examples where these heuristics are applied and really don't work properly. So one famous one is where basically all the heuristics are blown out of the wind, and at the end, I think it is white losing almost all of its figures, but still in the end having the move to checkmate the black. Yeah.
So in the previous slides, we have the features linear and assign orientation to each of the visual points.
Yes.
Is it often the case that we use this formula, or if there are other ways to combine the features into one?
It's a very good question. The question is whether this is the only way of combining the features. One of the next slides again says that we are looking into also learning those features and the combination of those features. And there you apply several tricks on how to combine those features into more features that are not necessarily linear. So it could be that others are better. And I'm not sure whether I've missed I think we're now in the end game, where you see that the queen is sacrificed now at this point. So basically here every heuristic would have told you that white is losing, but in principle he wins or she wins. And this is just a sort of historic game which shows that devising these heuristics in a game such as chess is very difficult. Here's another example where this is also in combination with the cutoff that I'm talking about, that you only look ahead a number of times, that you often have what's called the horizon effect, in that you say, if I look, how long do I have to look ahead, before I really can spot all the real problems in this situation that I'm in. And in this situation, if you can see this is a white pawn, and in the next step, so as soon as white has a move, he can turn this pawn into a queen and then win the game. Yeah, so it's only one move away. But if you would turn this into a search tree, then black has the opportunity to postpone this one move of white for about 15 moves. And that is by just moving the castle down and setting chess. So white has to move the king, and it can move it up, and black can make chess again. Yeah. So by moving the castle up and down, black forces white to move the king, but it can only do that 1, 2, 3, 4, 5, 6 times, and after 6 times, it loses the king. It loses the castle, so it postpones the bad news by 5. So if I would now have a cutoff function for my look ahead of 4, then as white, I would lose. I would not play the right strategy. And it's always the question, how long does my cutoff has to take? How much do I have to look into the future in order to still win the game? Which is another very interesting research question that you can ask yourself for your research paper that you have to write in the last week. So what is the relation between the quality of my agents and the cutoff length, the look ahead of my agents? And as I said before, obviously in the times of deep learning, we're going to look into how to learn these strategies. And obviously the victory of Go, in Go of AlphaGo would never have been possible without really training on examples or learning on the fly. That's what the later Go version did. By some kind of feature evaluation and learning of a heuristic function. And that's what we're going to see in 2 weeks, how this works. Now, this is the basic principles of how to deal with games that are far too long. So we have had one problem that the games can go on for so long that the length would be a problem. We're going to look into the breadth and the search space, size of the search space in about 5 minutes. I have two small sort of intermediate steps, and that's related to the question of chance in the games, but also multiplayer games. So what happens if we play with 3 players or more? Because this is the situations where we have this as well. And in principle, you can apply exactly the same strategy, but now you don't have one utility value, but you keep a vector of utility values. So here is a game with 3 players, and it's players A, B, C, and they play in an order, whatever, A, B, C, A, B, C, A, B, C. And all you have to do is to keep the values that the people want to maximize in a vector, and they choose according to all the options that they have as well. So if we would end up here in a situation where A could choose, no, sorry, this is a C move. So C moves here, and it can choose between those 2 states. It will look at the C value that it can achieve, which is the 3rd value in the vector, and it will choose the maximum one according to this vector. Yes?
Yeah, I have a question about 2 slides back.
Oh, yeah. Yes, this one?
It shows AlphaGo 1,202 CPUs, and does it mean that it took 1,202 CPUs to beat a human?
Yes, that was, I think, at the time the hardware constellation that they had.
Okay.
Yes, which is obviously a sort of technical gimmick because it would be different now, and I think the algorithms have improved. So you need fewer hardware, but this was at the time sort of the 2 sides that were pitched against each other. So going back to the multiplayer game situation, if you keep track of all the maximal values that the players could achieve, and suppose you want all of the players now to maximize their own value in this case, then you would say here, for example, that C chooses the one where the 3rd value is highest, so it would choose this one. And in these 2 cases, it would choose 2 because it's the other one is -1. Then it would be a B choice here, which means the middle value. And then it would choose between the 2 and the 1 here. It would choose this one. And then the A would choose between this value, which comes from down here, and this one. And of course, it would then choose this one as well. Yeah. So now you also have a strategy, but now in a game with 3 players, where A tries to maximize the first value of the vector, B the one on the second place in the vector, and C the 3rd one on the vector. Okay, so this is a sort of a very small parenthesis of, yes, here's also a way of looking at games where you have more than 2 players. Now the question is there also a way of doing this same with games with chance, with an element of uncertainty? And yes, there is a way of dealing with that. So here's, again, a very, very brief, just to give you a motivation, a quick glance of, yes, this also works. And here's the example from the game of backgammon. I don't know whether you know backgammon, but you have to move. You have 2 players, one with the dark stones, one with the white stones. And the white player has to move the stones from this half of the field via this direction to this field. So we are in an end game here of backgammon. And black at the same time has to move these stones in the other direction. And then there are some restrictions where you're allowed to put your stones, which I'm not 100% sure I remember. But the idea is that you throw a dice, and then you are allowed to move either one stone with both numbers or individually each stone with one of the numbers of the dice. So basically what you're allowed to do here is to move when there is a 5 and a 6 stone, then you are allowed to go 1, 2, 3, 4, 5, 6 and put your stone, your one stone from 5 to 11 with a 6. And it also says that there is a move from 5 to 10. And now I'm forgotten my rules of backgammon, namely if the 5 goes to the 10, there is a black stone, and I'm not sure, I think the black stone then goes back to the beginning situation. I think you throw out the black stone. Anyway, that's part of the game, that's not so important about this story now, but basically what it says is that you throw the dice, and then you see what are the possible moves that you can make given this space. So we can move from this space state here to another state by moving this to here, this to here. So that would be those moves. And we can also move from 19, this is this one, to 24, 1, 2, 3, 4, this is 5, would then go here. And from 10 to 16, yeah, we could also take this stone here, 5 to 10, and then from 10 to 16, and we could have one move from 5 to 11, and then to 11, from 11 to 16. Yeah. So these are all the moves that I can make with my stones based on this throw of the dice. And then the point is, of course, what is the probability of my opponent having a certain throw, because the opponent is next, so he or she throws the dice. And now I have to estimate how, because I can't take all the possible throws of the dice into account and calculate the full min-max. That would also be possible, but that is similar to what we're doing later with the Schnapsen. But you wouldn't do that in this kind of games, but you calculate the probability of a certain state being possible. And that is basically that you say, if I have, for example, a 1-1, then this is far less, or the probability of the 1-1 being thrown and 6-6 being thrown is half the probability of all the others, because I have only one way of doing it. Both of the dice have to be a 1, and otherwise both of the dice could be one of the values. So the probability of a 1-1 throw is 1 over 36, and the other one is 1 over 18. Yeah. So now I can take this probability into account when I build the tree by saying, okay, I have a chance node, and the chance nodes are arrived by some kind of chance factor, and then for each of those possibilities, I can now do what would my opponent do in each of the cases. So now I have, of course, far more states because I have all the states of my game, and then I also have all the possibilities given, labeled with the probability. So we can't really calculate the exact values anymore, but we can estimate some values with a given probability. And basically, you do that with the same basic idea of applying the min-max algorithm, but then when you are at one of those chance states, you just multiply it with the probability of this certain state happening in the first place. So basically, you have the algorithm, you have the same procedure, but you weigh your quality of your nodes depending on the probability. And that's just one very simple idea of dealing with this uncertainty of the throw, just to show you that it's possible to also integrate this notion of probability into the min-max algorithm in this way and other possible ways.
And that would also make it suitable for the first part or something.
That would make it possible. Yes, we haven't investigated that. I haven't looked into that because in principle, I think the probability for all the combinations you have would be the same for all the unknown cards. So you wouldn't gain any information. Here you gain the information because you have more likely states than others, because 1-1 will happen less frequently than 1-2. That would probably not be very useful information for giving you a good strategy, either here as neither. So, but there are games where this makes a bigger difference, where you can predict something about the quality, the probability of the states happening. But what we still need to do is, if the trees are now too big systematically, and there is one main algorithm, and the next step is what happens if we have the imperfect information as we have in Schnapsen, where the probability, the estimation of the probability of a certain state being reached doesn't really make such a difference in terms of the prediction of how you have to play. Yeah. So the main thing is now that the state spaces are still far too big, and part of what has been done is to tame the beast by having a more efficient way of implementing the Minimax algorithm by pruning the search tree. So only looking at parts of the search tree by some clever bookkeeping. And that's all it is, it's clever bookkeeping. So how we do that? We keep track of two values, namely the alpha value, which is the value of the best choice found so far at any choice point along the X path, which means basically, in other words, that it's the best value that max can achieve. And the beta value is the best value that min can achieve. Yeah? And that basically says that if we have alpha and beta, then we have an interval in which the solution has to lie. And this bookkeeping on these intervals is what helps us cut down parts of the tree. So let's go back to the example. In the beginning, we don't know anything. Remember that we do depth first search until we reach the first leaf. We start with our alpha and beta values not being restricted at all. Again, we call the recursive call for the min function. Again, we don't know anything, any restriction, but now it starts. If we find that the first leaf is a 3, then we know that it's min's turn. Then we know that the value that max will get upstairs, there up here, will never be bigger than 3, because min will always choose the 3. For this node, min will always choose the 3 or something smaller. So suppose here we get a 4 or a 5 or a 6, it will not change because min will always choose the left one. Yeah. So by knowing that we find one value which is a 3, we know already for the level above that the value can only be between minus infinity and 3. Yeah. So then the next one is we get a 12. Okay, doesn't change anything because we know that min will definitely choose the 3 or smaller, and we get an 8. So nothing changes, but now we know exactly. Okay, min will choose the 3. Now that we know that, we know as well here that 3 will choose something that's 3 or bigger, yeah? Because we have the 3 value that comes from down there, and whatever comes underneath on the right-hand side, max will always have the choice to go to the most leftward with the 3, so the choice for max will always be 3 or bigger, yeah? Is that clear? So that's an important sort of intuition that you need to understand. Okay, so now let's go on. We develop the tree further. We go to the first node in our leaf level, and we find that it's a 2. So what does it mean for those 2 nodes?
Irrelevant.
They are irrelevant, yes. Why are they irrelevant?
You can always choose a higher value.
Exactly. So there, we know that here min will choose something that is 2 or smaller. Yeah, it will never choose anything that's bigger. It would be stupid for min to choose something bigger. But then we know that max will never choose the one in the middle. Yeah. So suppose this is a value that's smaller than 2. What would that mean? It would mean that min would choose this value, but max would never choose it. So, because the value would only be smaller. Suppose it is bigger than 2, then min would not choose it. So, whatever the value of x is, bigger than 2 or smaller than 2, it would not make any difference. Which is very, very good news, because it basically means that we do not have to look at those two nodes. We don't have to, we can ignore it. Whatever the value of those nodes is, we can simply ignore it. So let's go on. If we find a value 14, then we get the interval minus infinity to 14. It is bigger than the, so we update our top interval. And there is still a possibility that the value is between 3 and 14, so we have to continue. We're not done yet. If it is 5, we have to update our values, because min would of course choose the 5 here, and then we would have to update this one here. And then the next one, if we would find something smaller, a 2, then we know that min would choose the 3, because the intervals would now not overlap anymore. And that's the alpha-beta pruning. And you would get the value 3. And the advantage is that you now have not looked at those two nodes. And in this simple example, yeah, so 2 nodes, who cares about 2 nodes? But remember what we said, we have a level that we look ahead. And it might now that we still have quite a big search tree underneath. So it's not just these 2 nodes that we don't look into, but it's all the children that we don't have to look into, because we know that no matter what we get here, it's irrelevant. So we can prune the entire tree underneath, and that is really can make a big difference. So here's now the algorithm. The algorithm is very similar to the Minimax algorithm, but now also does the bookkeeping about the alpha-beta values. So you initialize the v value to minus infinity, and you do the bookkeeping for the alpha and the beta. The alpha value is the maximum of the alpha and the v if you have a maximization. If you have a min value, so this is now the part where you maximize this as the initialize the v for the maximum of the min value. So this is a standard min-max as we did before, but now you can stop when there is the overlap of the intervals, which you do with the alpha, beta, and the v values. Yeah. So this is just the implementation of the principle that I just explained before. And of course, you need the mirror side, which is the min function, which has exactly the same, but then vice versa. So this one takes care of the beta side of the bookkeeping, and the other one takes care of the alpha side. And basically, what you do is always, when you do before you expand your trees, you check whether the intervals are still have an overlap or not. And this is what this implementation does. So the important thing about this pruning algorithm is that it doesn't affect the final results. So it is not that we calculated an approximation. No, we calculated the precise result, because the nodes that we cut, that we ignored, didn't matter. That's the basic thing. So we only looked at nodes that wouldn't have made a difference anyway. And those are the ones we prune. We can prune entire subtrees. And it's very, very important that we have that we do this pruning in the right order. So if we know somehow the ordering of the nodes when we do the evaluation, then this will also help us. So if you always start with what you think is the smallest one, then your chances of pruning become far higher. So it's very important that you also look into ways of ordering your nodes. And if you do that perfectly, which is obviously impossible to do as it's heuristics. But suppose you were able to do that, then you would get a time complexity that is b to the power of m half, which actually means that you can go 2 levels, so twice as deep in the same amount of time. And as I said, thinking about the horizon effect, where it really makes a difference at what point you stop, going twice as deep in your search and in your prediction is a very powerful means. So alpha-beta pruning is really a must if you want to not just be faster, but it means that you can go twice as deep in your prediction in the same amount of time. I think that's really the importance of this algorithm. So basically, yeah.
I have a question. What theoretically would happen if you play against like a kind of fixed algorithm who doesn't take the optimal choice? So basically, we cut off the branches, and the algorithm doesn't take the min value. So we lost that information, right? So what would happen to the algorithm?
I wouldn't know why you would lose the optimality, because the pruning is only about things of which we are sure that they are not that they are not better. That's otherwise we wouldn't prune them. So I wouldn't know of any way of how you could trick things into tricking the alpha beta. I don't know. That could only probably. But the calculation of the strategy is offline before you play, and you would always take the worst anyway into consideration. You always take the worst playing of your opponent as the starting point of your choices. So even if they play better or even worse than worse for you, so even if they play better for you, it would only make things better, and you could prune. No, you haven't pruned anything anyway, but you wouldn't play worse in any case. So maybe I understand the question not incorrectly. Okay. In the interest of time, I have to move on because I still have some material. Because the point was now that we now managed to deal with the length of a game by just saying we stop after n moves. That was the first thing. Then we said, okay, but still the choices might be so big that we have to choose, that we have to reduce the search tree, for example, by doing the alpha-beta pruning. We had the reasoning with chance, but in a game such as Schnapsen, in the phase 1, this doesn't work because we have the uncertainty about how this game, where are the cards? So basically what we now do is look into a problem of search with only partial information. And there's also strategies. And the vocabulary for that is introduced in this sort of general framework. And that is if we only know parts of the states and the actions. That could be that we simply don't know whether something is true or false. It could be if we are in exploratory phase of the game where every step reveals new things. It can even happen in a completely sensorless problem. So I don't know anything about in which state I am and so forth. So let's look at this sensorless problem to introduce the idea of yes? Back to our first lecture or second lecture of the hoovering problem. But now we have a hoover that isn't capable of measuring whether it's dirty or not. And it's not even capable of knowing whether it's in the left room or the right room. So the question is, can you still apply search to find a strategy to clean or to find a path to clean the whole 2 rooms if we have no sensors at all? And the answer is yes. It's a very expensive one, but we can do it. Because if you look at those 8 states that we have, there are some generic properties that we can see here. We know, for example, that if you are in one of those states and you move to the right, you end up in one of those states. Yeah. So in whatever state you are, you move to the right, you end up in 2, 4, 6, and 8. Yeah. If you have a certain action, right, suck, left, clean, then you know that you end up in 7. Okay. So when the world is not fully observable, let's reason over the states that you could reach. And how do you do that is what is called the belief states. So belief states are sets of states and possible states that you could reach given a certain action. If there are S number of states, then we have 2 to the power of S states. So it really becomes now extremely expensive, but we can deal with things. So this is now the belief state of the vacuum world, where basically we have one state where everything could be possible. We don't know anything. So that's the complete state of ignorance. And then the point comes, if we move from the state of ignorance, we end up in a state, if we move to the right, we end up in any of those 4 states. If I am in this state where I'm in one of the here, and I move to the right, nothing happens, of course. If I clean, only 2 states are possible. Yeah? So basically, I have now the belief states, which are each of those boxes here, and I can still come up with a strategy that gets me from the state of complete ignorance by taking some actions to one of the goal states. Yeah. So in principle, it's the same idea, but now we do our search not only on the states themselves, but we do it on the belief states over the states. Of course, as you can see, as I said before, we have now 2 to the power of S states. So when we start with 8 states for the hoovering, then there are many, many, many states that we have to do our many belief states. But as you can see here, there are not that many that are relevant. Yes? Schnapsen? So this is now the situation where we are, and the practical example that we applied is Schnapsen. Having said that, we're not going systematically through searching through all the states, the belief states. In Schnapsen, you're absolutely right. This is not working for Schnapsen because there are so many belief states that this is not efficient. But what we're going to do is that we go to those belief states and we're going to do random sampling over those belief states. So we are turning now from a fully observable game where you can systematically find more or less all the strategies to the goal. We have to move to something that's either learned, or we have to move to something where we do statistical analysis over those belief states. And that is the move that I'm suggesting here. That one way of doing this is to, and that is, I think, one of the bots that we gave you is the RDeep bot. And what RDeep does is basically that it takes or goes over all these belief states, takes one of them and plays a game randomly, or plays 8 or 10 games, and then it averages over the performance over those games that it has played, and that gives you the value of the quality of the state. Yeah. So we turn these belief states now into a statistic measure of the quality of the games. And that's the only thing we can do. So basically, if we started out with, please give me 2 more minutes, if I may. We started out with the question: what is with Schnapsen? Is it really an imperfect information game, perfect information game, and is it deterministic? We have now the game engine, and the game engine has the full information of the game states, of course. So what we have is a representation of all the cards. And we know for all the cards where they are. We know whether they are with min, with max. So that's X is max, with I is min. And then we have the position in the pile. Yeah, we still have the pile, and then we know that this one is in position 1. So that is our representation of the game. And then for each of those games, we have states where we can move from one state to another. The player itself, the bot, is given an imperfect part of this full information game. Yeah. So this is what your player gets and what you have to work with. So instead of the information that the game engine obviously has, because we know what card is where, but the player doesn't, so you get all these 14 question marks in the implementation of the box. And with these, you now have to do some kind of manipulation. And the rhetorical question is, will min-max work? In phase one, no, it will not, because if you would want to play that, you would have to do it over all possible belief states. And that is far too complex in terms of complexity, time, and space. So we need to move into more statistical analysis. And so what the idea is, as I said, this is our deep algorithm, or later some perfect information Monte Carlo sampling. There is a paper on the Canvas page which also goes about this perfect information Monte Carlo sampling. Basically what you do is that in the first phase of the game, you have to go through all the possible belief states, make some random choices, and then in the last phase, you can go back into the min-max mode, and then for the last 5 cards, you can choose the perfect strategy. But that is something for the third week to combine those two ideas of first some random sampling over the belief states that you could have, and then in the second phase do the systematic min-max algorithm. But this is now really moving into the research part that we're going to deal with in week 4, and we'll spend more time next week on that. For this week, I think it's important that you really understand the min-max, implement it in practice it in the working groups tomorrow, implement it for the milestone 2. Also do the alpha beta pruning, because it helps you look ahead far more. And then next week we look into questions, how can the human-like knowledge help us for this? So good luck with the working groups and computer practice tomorrow, and see you next week.